Hello everyone, my name is Mohammed Syahmi, number matrix A25CS0092, and I'm part of the group doing COA performance benchmarking project. So for this video, I'll be walking you through Crystaldiskmark, the tool I personally handle for our group benchmark. I will show you how to actually run the tool, how to pull out the performance metrics for our two workload, which is workload A and workload B, and then break down what those numbers actually mean. So let's get into it. Okay, so here I downloaded the Crystaldiskmark from this SourceForge.net project website. So I already downloaded it, and let me just run it real quick. Crystal. Yes. Okay, so here, let's open my report. Let's go through. Okay, so before that, the details on installation and configuration for this tool, which is Crystaldiskmark, you need actually at least Windows 10 or Windows 11, but Mac OS also supported. And then the storage can be any internal or external drive like this: SATA SSD, NVMe SSD, or HDD. And then this space approximately 10 MB for the application. And then here the installation steps I already showed you. I downloaded it, just run the installer and then launch the exe file. So let us go to the configuration for workload A. I go to settings, I choose NVMe SSD, or you can manually configure by setting the block size to 4KB. And then I go to the settings. Okay, so for workload A, I'll be using this RND4K Q32T16. So which is here, this line, RND 4KB, or this is the block size, and then the Qs, which is 32, and then thread count is 1. And I will also setting the sequential part, which is for workload B, this line, the sequential one. Let us see, which is, okay, here you can see I circle it 64 KB. Q1 T1, Q1 thread 1, press OK. Okay, now both workload are already set up. Let us run line by line. So I'm gonna run the row for workload A first. While waiting it run, I'm just gonna explain it to you, a quick rundown of what is this tool actually does. So it's actually a synthetic storage benchmark. It writes test data to your drive in different patterns, sequential or random, big blocks or small blocks, with different numbers of commands queued up, and measures how fast your drive handles each pattern. So before doing anything, you need to configure it first. So I already did. Oh yeah, before I forgot to tell you that I set the iteration to 5 and then the file size to 1 GB. Okay, it's done. Now I go for sequential 64, which is for workload B, and then we will compare the value. You can see I use the Crystaldiskmark 9.0.3, so it will run as admin and you will have full access to the drive. Okay, so now this is the value. Okay, so to differentiate these values of read and write by using this table. Okay, I hope you can see this. So for the workload A, we got the read value, which is in megabyte per second, which is 374.39, and at the write value 311.90. So this is the read throughput and the write throughput for workload A. It is different from in the report because our drive performance doesn't always provide the same performance every time we use them. So hence that is why the values are different from this demonstration and in the report. So this is the result for the test workload A. Now, as you can see, we got the read throughput for read and write for workload A is this and this. So megabyte per second, these values isn't the only metric that that matters for COA. What we really care about is actually the IOPs, which is the input and output operations per second, because that tells us how many individual performance or operations the drive can handle, not just how much data can move. And then the formula is IOPs equal to throughput in megabyte per second times 1024, and then divide by the block size, which is in KIB. So here I already calculated and give the answer the table, but this is for the report, which is different from the demonstration value. For workload A, 374.39 times 1024 divided by 4, we got 95,843. Okay, so for the test 1, here 374.39 divided times 1024 and then divided by the block size, which is 4, we will get the answer 95,843. While workload B, I got 33,741. And that is the whole point. High queue depth means the drive controller can juggle tons of operations at once. And then we can also calculate the average latency, which is here, as you can see on the report. We just calculate 1000 divided by the IOPs. So the point of this is actually, it's not, the values actually does not matter in detail, because we want to see interesting has already happened. Because as you can see here on the report that I already did, workload B uses bigger block, which is the 64 KIP, but its IOPs numbers are way lower than workloads A, because that is the metric. And the biggest takeaway is for the workload A with tiny 4 KIB blocks but a deep queue of 32 commands across 16 threads, that actually outperforms the workload B's with the bigger 64 KIB sequential bucks, both IOPs and even raw megabyte per second. Why? Because modern SSDs aren't just one single channel, they have multiple NAND flash drives and channels working in parallel. So when you queue up 32 commands at once, the controller can spread those across different channels and overlap their latency. But at queue depth 1, every single command has to fully finish before the next one starts. So you're stuck waiting on the raw exposed latency every time. So this is exactly why command queuing, NCQ for SATA drives, or the multiple queues for NVMe is such a big deal in storage architecture. It's the difference between a drive that looks fast on paper and one that's actually fast under real multitasking conditions. And also there is something that is worth noting. Write speeds always beats the read speeds in both workloads. That is because the SSD RAM or SLC write gauge, it absorbs incoming write super fast before flushing them to the slower NAND later. So short benchmark runs like this one makes write looks faster than they'd be in a long sustained transfer. That's everything for my part on Crystaldiskmark. Thanks for watching.